the sum is supposed to be equal to 1. The sum of all probabilities should be equal to 1. And k value here is equal to 0.1. Okay, it is supposed to be equal to 0.1. So actually, in a tabulated format, I have my joint probability mass function as like this. So x can take 0 and 1 values, y can take 0 and 1 values, and the joint probability mass values at every corner are like this. Now, I need to determine the marginal distributions, the marginal probability mass functions. And when I determine the tabulated format here, the marginal probability mass function of x is going to be equal to 0.3 for x being equal to 0, which is the sum of that row, and 0.7 for 1. And the marginal probability mass function for y, for value of 0, it is 0.58, and for value of 1, it is 0.42. So I have determined the marginal probability mass functions and the joint probability mass function. Now, all I need to do is this. I need to check if this equation is true for all possible values of x and y. If it is true for all possible values of x and y, now how many possible values do I have? There are 4, right? So there are 4 possible combinations here. I need to check 4 corners if this is true or not. Now let's check. Let's just say, let's try if this equation is true for 0. Now, the marginal probability mass value for x at 0 is 0.3. And the marginal probability mass value for y to be equal to 0 is 0.58. So the product of these two is equal to 0.174. What is the joint probability mass value at 0, 0? It is 0.18. And unfortunately, these two values are different from each other. Now that they are different, now that this equation does not hold for this corner, we can immediately say that x and y are not independent. Because if in at least one case, so it says here, if for any real couple of x and y, this inequality is satisfied, if this equation is not satisfied, if they are unequal to each other, in that case, we say that they are not independent. Okay, they are not independent. So x and y are not independent in this question. That is very short. It is a very short answer. How about this one? How about this one? We have the joint probability mass function of two Bernoulli random variables again, x and y. Again, we have the joint probability mass function in the tabulated format. Are x and y independent? The question is asking this. Are x and y independent? Now I am going to answer this question like this. I'm just going to compute the marginal probability mass functions in the first place. And after computing the marginal probability mass functions, I'm just going to check in all 4 possible cases, because there are 4 possible cases here in this tabulated joint PDF, joint probability mass function, if this equation is true or not. Now let's check the 0, 0 corner. The marginal probability mass value for x at 0 and y at 0 are respectively 0.4 and 0.25. And that is 0.10. And the joint probability mass function at 0, 0 is 0.10. So this is true. For this corner, that is true. But remember now, we need to check all corners. For any of the corners here, if any of the joint probability mass values, this equation does not hold, then they are not independent. Now let's see the joint probability of x at 1 and 0. 1 and 0 is 0.15. So at 1 and 0, it is 0.15. And the marginal probability of x at 1 is 0.6. And the marginal probability of y at 0 is 0.25. When you multiply 0.6 and 0.25, again, you get 0.15. So this is true for this corner as well. Now let's just check the corner here. By the way, I am saying corners here, but actually what I mean here is all possible cells in this table. So if we have, for example, a 5 times 5 table here, then we need to make this check for 25 cells, not just the corners. Okay, for all 25 cells, we need to check it. However, there is another easier way there. Okay, there is also an easier way here as well. Now, let's just check that cell. The joint probability at 1, 1 is 0.45, and the marginal probability of X and Y respectively at 1 is 0.6 and 0.75. If you multiply these two values again, you would get 0.45. So again, for this cell, we have an equation. We do not need to check the last cell, my friends. Automatically, it would be satisfied. Why automatically it would be satisfied? Because we know that some of the probabilities are equal to 1. Okay? So the last cell will automatically be satisfied. So because that equation is satisfied in all possible joint probability mass values, we say that X and Y are independent. However, there is another way of checking that. In this table, if all of the rows are linearly dependent to each other, so you know the definition of linear dependence from linear algebra, right? So imagine now this table is a matrix. If all the rows are linearly dependent on each other, then we say that they are independent. These random variables are independent. If all the rows or all the columns, are linearly dependent on each other, then we say that these two random variables are independent. For example, what is the first row? It is 0.10 to 0.30. What is the ratio of these probabilities? 1 to 3, right? So the proportion between these two values is 1 to 3. And that proportion is the same in the second row as well, 1 to 3. Similarly, in the first column, we have 2 to 3. The proportion in the first column is 2 to 3, and that proportion stays the same in the second column as well. So because of that reason, if in all of the columns or if in all of the rows we have linearly dependent rows or linearly dependent columns, then we can easily say that they are independent. But for example, here they are not linearly dependent, right? What is the proportion in the first column? 3 to 2, right? 3 to 2. But that is 4 to 3. Or in the first row, for example, we have the ratio of 18 to 40 or 9 to 20 simply. But here we have the ratio of 4 to 10 or 2 to 5. Okay? So these proportions are not the same. Because of that reason, they are not independent. These two random variables are not independent.